This video is going to cover the topic of nuclear chemistry, just in a sort of an overview, the big topics. Well, first of all, nuclear chemistry just means the chemistry of the nucleus. So I kind of drew a very terrible picture of a nucleus here with a proton, and these shaded ones are neutrons. So this would probably be an isotope of hydrogen, like tritium, because it has one proton and two neutrons, tritium. And there can be different types of isotopes of different elements that are natural, and they can be radioactive and have different types of radioactivity, and it gets complex. We can also have beyond the natural radioactive isotopes of elements, which are usually on the lower part of the periodic table. You can also make some radioactive elements out of less elements from the top part of the periodic table, like fluorine. Fluorine does not have a natural abundance of radioactive isotopes to any great degree, but we can make some. So you can take fluorine atoms and shoot them with a lot, I think, neutrons. I can't remember what they use, but they can make a radioactive form of fluorine called F18. It's the isotope of fluorine that's going to be radioactive, and it's actually used in medicine. So they radiate this natural fluorine, it becomes a radioactive form, F18. They can do some organic chemistry really quickly to make fluorodeoxyglucose. And once they make that, they have about, 109 minutes, or a little bit more than an hour, maybe an hour and a half, to use it, because it starts giving off radiation. What type? It's called positron. So this F18, and you'll sometimes see when we refer to a radioactive element, we'll have the element and its kind of atomic number, its mass number, F18. So we can say, well, this emits, this F18, a positron, which is basically an electron with a positive charge. So it goes out from the radioactive isotope, and it meets electrons that are just naturally abundant, that are negatively charged. And once they hit, it emits a lot of energy. Well, the reason that you can use this then is because if this glucose, which has the fluoro group, that's radioactive, it binds well to cancer, because cancer is a fast-growing cell, then it concentrates. And if it concentrates, once it emits that positron, a lot of positrons emitted hit nearby electrons, that can be a natural radiation source from a particular spot in the body. And they can say, oh, there seems to be something that's concentrating all that fluorodeoxyglucose. It possibly is cancer, and they'll know where to investigate. So it's been used extensively in what's called positron emission tomography. And there's different types of radiation. Elements with atomic numbers higher than 20 usually have one or more isotopes of an unstable nuclei. When we say unstable, we mean radioactive. And when we say radioactive, there's kind of two issues here. There can be what kind of radiation do you get? Gamma, for example, is a very high form of energy that can be dangerous. So there's the type we have to worry about, but there's also the intensity, the rate of radioactive emission. So that's a half-life thing. So, for example, this is amazing. The one we just showed, that fluorine 19, that's like 109 minutes. But if you take uranium-238, much bigger, its half-life is like 4.5 billion years, like the age of the Earth. It's just amazing how different you can have elements as far as their half-life. So anyway, we can just kind of remember there's different types of radiation, and there's different types of rate at which those types of radiation come off. All right, there's different types of radiation, we said. There's two, particles that are just really particles. They're not electromagnetic radiation, or what we would kind of relate to light. They're alpha particles, and alpha particle is just a helium particle that has a +2 charge. And typically, if we write the isotope in this way, instead of using these sort of notation, what we're saying is the charge is kind of on the bottom, and the mass is on the top. Let me just put that in here. Charge is kind of on the bottom, and we're saying it's a +2. And the mass is on the top. We have 2 neutrons, and I'll just kind of abbreviate, 2 protons. That's what you have in an alpha particle. So we can call it a helium ion with a +2 charge, or you can refer to it as an alpha particle. It's the same either way. And boy, if this hits you, I'm trying to show my finger. It's trying to get off energy. It gives off a lot of energy. The good side about this, though, is if it doesn't get in your body, it's not very penetrating. So skin is not real sensitive to, I guess, damage, but your liver, of course, your lungs, there's tissue issues. So some tissues can be more sensitive to radiation, and some tissues can be less, more sensitive to radiation. Some can be less. So if it's on the outside, that typically is not going to hit something that's very sensitive to radiation. So that's the one good thing about alpha particles, is they don't have penetrating power. Beta particles are just high energy electrons, but please know we can have what's called a beta plus. It's that positron that F19 kicked off. You can see it as sometimes a beta plus, or they'll write it as electron, no, sorry, that's a little bit bigger. They'll write it as electron 1 is its charge, and a 0 is its mass. So positrons, beta particles are pretty much the same. They're just either positively charged electrons, which is kind of weird, and a negatively charged electron. And then you have, like in most intense electromagnetic radiation that you can imagine, is gamma rays. So of course, like the Hulk was exposed to so much, and that was a good thing and made him stronger, but usually that's not going to be a good thing. It's going to just fry the inside of your body, the outside of your body. It's pretty bad stuff. Now we said that the top of your periodic table kind of is free of any naturally unstable radioisotopes. But you get past your lead and you start getting into very high natural abundance of radioactive material. This is kind of important because when you get into concrete and building houses, there's going to be some natural amount of heavy metals in that concrete. So everything kind of has a little bit of radioactivity in it, even you. So, all right, so there's different types, we said, and we talked about a little bit of the alpha, beta, and gamma. So I kind of have those summarized here. The alpha particle is big. The beta particle is an electron, or it can be a positron. And of course, that very, very high energy photon is a gamma ray. Now, it's interesting, a lot of the emissions, whether it be alpha, beta, or gamma, let me just pick on these two. If it's alpha and beta, you often see along with alpha and beta emission a little bit of gamma radiation or emission. You can maybe think of it like this. If I were to maybe I'm going to use some candy here. When you have things adjusted in the nucleus, so I'm just going to put this candy kind of spaced out in my hand here. So I guess, looks like I have yellow and orange. So let's say this is my proton, and it's going to kick off a beta particle. It's going to become a neutron, and my neutron is yellow there. I got to get another yellow here. Yellow is right there. That's my neutron, and the orange is my proton. So when this one just suddenly up and decides, and you can't predict when they're going to do it. It's the coolest thing. You do not know when they're going to emit. You can kind of get a measure of how much they emit over a certain hour, but you don't know when the next click in your Geiger counter is going to go off. It's the coolest thing to me. So this is our proton, and it's going to kick off some beta particle that has a positive charge. Well, if it's positively charged, remember the protons are positively charged, then it's going to change into set that aside, a neutron. So you're going to get the same mass is going to be maintained, 4 kind of skittles here, but we went from having a proton to having now another neutron. Well, here's what happens. When all that happens, these kind of like vibrate a little bit, or just kind of reshuffle and resettle in and repack. And when that happens, when you get kind of a repacking, I'm trying to vibrate my hand here, like repacking, you kick off a gamma emission. So you typically have, along with these alpha and beta emissions, some amount of gamma emission, which can be bad, because of course this is very penetrating. Alpha can't get through skin, this barely gets through skin, this goes all the way through your skin to the other side of your skin layer. And it stops every now and then along the way and drops its energy in a very, very big way. All right, I went ahead and showed, and we're not going to get into, this is more general chemistry stuff, balancing nuclear reactions. But I just wanted you to note here, like if you see the alpha decay has been proposed, this is our atomic number, or sorry, this is our number of protons, which is like our charge. This is our mass number. And we can say then that the number of protons is kind of split up. We have 2 protons that went with the alpha particle and 90 protons that stayed with the nucleus that was uranium. But it has to change because remember, the identity of any atom is determined by the protons. So when we see this lower number, I saw earlier it was for particles that are kicked off, it can be charged. And for those that, the elements, it can typically be the number of protons. And so we see our mass number dropped by 4, 238 to 234. For carbon, we can have an electron kicked off. Remember how we said if you kick off charges, you tend to change the proton to a neutron if it's a positron? Well, it's the opposite. If it was an electron that's kicked off, we're kicking off a negative charge. So we're using a neutron that becomes a proton. So we're going to take a neutron that's part of this number here, and we're going to make it jump down to this, adding up to this number because we're making another proton. So basically, whenever you kick off a beta particle, you're making another proton, and that number on the bottom has to go up. This number on the bottom has to go up. So you're going from a 6 to a 7. But this number changes because you're just, again, changing a neutron. It's supposed to be a neutron into a proton. And last, the positron, we already said if you kick off a positron, or you can note it as a 1 and a 0, that's the same thing. We kick off a positron, we make fluorine, because again we're now going in the opposite direction. This, if you kick off a beta particle, this number goes up, the bottom number. But if you kick off a beta plus particle or a positron, this number goes down. Alright, that's a very quick rush through it, and I probably should have had more time on it, but just know that we can sometimes use our knowledge of what's kicked off to determine what's left as an element. Thorium is made from uranium's decay. Fluorine is made from neon's decay. And nitrogen can be made from this carbon-14 decay. Alright, I think we're going to go a little bit faster. So alpha particle, we said, can be represented like this. The beta has that charge on the bottom. It's noting it, that's just an electron. Basically, a beta particle is an electron. The positron is a positively charged electron, so we have a positive charge. Gamma does not have any charge, and it does not have any mass. And we'll skip these two. You can have proton and neutron emissions, but these are the ones that, the 3 that are often asked that you know. The 4. These kind of being the same. They're beta plus, beta particle, and a beta plus. So these are the 3 I want you to know: alpha, beta, and gamma. There's a good video if you have the PDF of this. The symbol for alpha again was our just symbol like this, and the radiation with a mass number of 0 and an atomic number of +1. That should be a charge. That was then our beta particle with a plus charge. Or we can say electron with mass number of 0, but a charge of +1. That's our beta particle. So alpha particle, beta plus particle or positron, and then the gamma was that symbol here, and you can sometimes see it written like this to note that it has no mass, it has no charge. Almost done. We've said the alpha particle can't go too far, paper can stop it. Beta particles can get stopped by just an aluminum layer, but those gammas can go through paper, aluminum, concrete. You need something like a thick piece of lead, and even then some of it still gets through. There's different ways because of the different penetrating powers of these particles, and even sort of the different issues with the tissue, being some tissues more sensitive than others. We have a whole lot of different measurements. But please just know this, that cells are the issue, how they get hit, and ionizing radiation is kind of what we're talking about. Radiation that will ionize or break bonds. The most sensitive types of cells are those in your child that's developing, or the baby in the womb. because those cells are, multiplying or splitting and growing very, very quickly. There's two types of basic radiations, and we're going to just say that there's the amount of absorbed, into the body, but there's also this kind of issue, that's the amount that gets absorbed into your body, and there's even the issue of how much is emitted. So you can kind of think of it on three levels: how much is emitted, how much is absorbed, and by what tissue. The tissue issue, what kind of tissue. So we're going to have a video on this in our lab. There's measuring how much is just emitted. I didn't even put in here the type of emission you're dealing with. How much is absorbed and by what tissue. So there's actually kind of four. How much, or what is the source, how much of it is emitted, how much of it gets absorbed by the body, and what kind of tissue are we talking about that's absorbing it. The one that's most important is the sievert. You need to know the sievert, and we get about 1 to 5 millisieverts per year just living on Earth. So they kind of give you a different, unit here. But ground, air, cosmic rays, everything has a little bit of a source of radiation. We'll talk more about the sievert in lab. I talked about half-life. Remember that fluorine 18, was 109 minutes. So we could say that for fluorine, if this is in hours, it was about right here. Oh, that's cool. I think, just read my graph. This is for fluorine because it's at half its value that originally had 1 as an amount percent. It's at 50% at 1.5 hours roughly. So we can do the same thing. It's going to be at half of that. It'll be about 0.25 in another hour and a half, and then you just keep on going. So of course it kind of has this drop where it's not linear, but you get down to low amounts pretty quickly with fluorine 19. But again, for uranium-238, its half-life was 4.5 billion years. That can be very, very long before you get to that point here. Because of that long decay, we can use that in dating sometimes, like carbon-14. It's a very, very slow decay, very, very long, very large half-life. We can use that in dating materials that we find on the Earth. Hey, I'm going to stop there. Thank you so much for this crash video, or just rush through nuclear chemistry. There is really some really important work going on with fission chemistry, and that's the breaking apart. That's your basic nuclear reactors that we've had. But there are also some ideas of fusing together, like hydrogen, to make a heavier element and have the energy from that. That's a fusion reaction, fusing together. So there's some energy. There's some work going into that. It's a lot of work, a lot of research that's going into trying to make fusion nuclear energy reactors.